Yeah, I'll post the recording later. Uh, Everybody has, you know, can see the slides, right? I'm sharing the slides. Yep. Okay. Uh, so what I would like to talk about is actually the concepts of creativity and active inference in the context of free energy. Now, one of the issues when talking about these topics is that usually I don't want to say that they're considered more advanced technologically or mathematically. It's just that you can learn a lot of techniques without kind of diving into kind of the conceptual or the cognitive or philosophical aspects of it. And I'm kind of taking the other approach. We'll talk about the big picture and the concepts. But since our main motivation is really musical and creative, I would like to start this with a little kind of, I don't know if a challenge, but with opening with a question. So I don't know how many of you are familiar with this painting. No, I don't know if I can see everyone. Uh, if somebody is, then just feel free to open the mic. You can see also that the artist who signed on this thing is called min max expectations of log dx plus expectations of log 1 minus djz, which means that this is a computer program that actually generated this painting. And the reason I kind of bring this because for those who didn't follow this kind of little bit of a provocative question, a piece of news. Uh, in 2018, this piece was sold at Christie's for this tremendous amount of money. Where initially nobody actually, the creators of this piece didn't think about this. Um, and then the question is, well, what do we call art? This is really just a computer generated uh, image. So what is it worth? Well, if this is the way we evaluate art by how much it sells in auction, apparently it is valued. And now the thing is that this portrait, which was AI generated, piece of art, was done by a program, a neural network, and sort of the human story around this was that the code, which is kind of part of the tradition and the common practice today with computer science, is that people share their code. So Robbie Barat was the person who actually created the code, but he put it online for free. And then there were three French students who borrowed the code. They even consulted them, and then they used his code to make this painting, and they made this piece, and then gained a lot of money from it. So there was even a question of ownership of this piece of art, not only the creative part, but somebody else owned the code, but then the artifact was done by somebody else, and the artifact was pretty cash worthy. So kind of the question is, yes, the art can make, well, sorry, computers can make art, and a lot of the images that Robbie Barat's original neural network, which was this generative adversarial network. We have one paper at least about this specific technique. It was trained on images of people. It could be faces, it could be nude images, depending on what he was trained on, and then it was used to kind of twist stuff and generate kind of random versions from parts and limbs and structures that it learned. Of course, it didn't learn them in a way that would imitate. It could be more abstract, it could be more photorealistic. And normally we see a lot of kind of deep fakes where actually the goal is really to create an image that you would not distinguish from maybe true image. So the whole deep fake issue. There are others like style transfer where you can use them just to stylize images, but you can, the reason I'm bringing this example because it almost seems to be sort of like an expression, right? It has kind of its own style. So you can use these networks in ways that they create something that you would normally attribute to a human kind of intent, creative intent. This is not just an imitation or coloring or stylizing an existing image or trying to fake something which is photorealistic, but it almost has some sort of a emotional impact here, right? The shapes, the colors. But frankly, it was, again, a machine that was randomly learning parts of images or paintings and then recombining them in novel ways. So kind of part of the question is if we think about machines, but again, this is not necessarily, or it's not meant to be a computer music class, but just a machine as a formal way of or algorithms, right? So algorithms basically a set of instructions that could be operated by a machine. So if a machine is creative in some sense, so computer programs, we would call them maybe creative if they're simulating human level of creativity. Now, why we'd want to study such a thing is, of course, to understand our own creativity, and then formulate algorithmic perspective on creative behavior in humans, and also to interact with the machines in creative ways, so it can enhance human creativity, either with or without the machine. So the machine itself doesn't need to be creative in that deep sense. It can be creative in shallow sense. And people actually try to define different levels of creativity. But I wanted kind of to use this as to set up the premise for the discussion. And now, if you think about interacting with a machine like this, we have, first of all, some kind of action that has to happen. And this action maybe has to follow certain logic or certain structure in the machine, but it might also imply some structure or some logic or some process that goes on in the human brain who interacts with it, or this could be the composer, it could be the audience. So in some sense, that machine and its environment, which is human, okay, have to interact in some way. And if you think about some dynamic or interactive models of creativity, of course, there are questions that are relevant for AI, for cognition or music cognition. The general question of computational creativity is actually the points that I showed in the previous slide. Generative art, and the whole question of procedural content generation, which is kind of a different name, or more broad than algorithmic composition or compositional algorithms, which also includes a question of improvising with machines, so-called music meta creation, which could be, part of this is also computer-aided composition, but in other interactive contexts like computer games, the PCG, which is a term that comes from computer games, also applies to music. So if music has to be created based on actions of somebody who's playing a game, and these are all models that we kind of need to consider. So and so the underlying concept or the basic principle, if we think about our own brains, and then this is how we will also model the artificial, if you want to talk artificial brain or artificial model for learning music. So there's this concept of the Bayesian brain. And the underlying idea, which is dated back all the way to 19th century by Helmholtz, is that actually there is an active aspect of perception. So it kind of suggests that there is sort of another little kind of man or some entity in our mind that creates some hypothesis or predicts stuff, and it takes evidence from the sensory modality and eventually makes a decision if some hypothesis that it had is true or false. So this kind of a logic decision making is the inference part, and it happens according to Helmholtz, or his kind of idea is that this is what the brain does. It basically sits there and does little accounting or decision making, and it's done even unconsciously. So we don't need to do this in situations where we actually have to come up to an explicit decision. Everyday perception, anything we do, sounds that we hear, images that we see, also could be considered decision making. It's just done in unconscious way. And we will relate this to active inference, where the idea is that the brain is active, which means it can select its own perception. And this is also a very important aspect. Our agents can act on the world. You can select your own sensitivities. You can select your own evidence from all the sensory information that basically pounds on your senses, on your ears or eyes. And what we hear is also a selective mechanism. So we actually predict things or we imagine things, and then we try to fit what our senses provide to our imagination. And since we can choose what we listen to, there's an active, one of the examples is saccadic eye movement. And the question is, who is controlling what? Are we, when we look in an image and our eyes jump all over the place, how is the scanning done? Is the scanning done before we perceive what the image is, or we imagine something and then we kind of run our eyes on an image in a way that actually conforms to what we expect it to be? So when we listen to music, do we hear things that we actually anticipate, and we ignore things that actually don't conform to what we would be trained, either culturally or in terms of some sensibilities that we have? And whatever doesn't fit this model will be sort of just noise or ignored. We might not be hearing this at all. So the active inference is the idea that we do this unconscious inference, and we can also decide what evidence we bring in and what evidence we might ignore. So the act of perception is kind of an active way of sampling or taking evidence from the world, and we want to maximize the evidence or minimize the surprise. So if we try kind of to give some examples, for instance, if we see here, the, whatever we call it, Star of David, it's not there. I mean, there is no such, what you have actually is these black Pac-Man kind of circles, right? And then you have these triangles, and sorry, kind of jumped forward, right? The fact that you see a shape here, this shape doesn't exist, right? You kind of complete this in your brain because most likely you're familiar with this shape before. So you kind of combine this evidence. Of course, you can also use this as an example of Gestalt psychology and other phenomena. But kind of the point that I'm trying to make here is that you infer a pattern from a bunch of unrelated evidence because you know that this pattern can exist. So if this example is a little schematic, anybody knows what we see here? I mean, people who are familiar with this example probably know this immediately, but those who don't, can somebody tell me what we see in the picture? Just open your mic. I mean, it's a lot of random black and white dots, but can you see something?
Looks like a dog photo.
Yeah, it's like a Dalmatian, right? So you have here the ear and the face and the collar and the legs, and here's the leg. I mean, there's a lot of details missing, right? But you can kind of make up this pattern. I don't know what, this probably also has some kind of a pond-like, I don't know what it is, kind of a wheel, but this dog is definitely something that once you realize that it's there, you immediately see it. Right? So, the sensory information or whatever your retina gets is basically just a bunch of random shapes. So the fact that there was this little man in your brain that tried to simplify this and understand what's going on in this picture is kind of an example for this Bayesian inference. So what's Bayesian in this? Um, Actually, maybe I kind of jump to my slides before talking about Bayesian statistics. So my original intent was really to go and go through one of the um, articles, Medium blogs that I put on the website that talks about Bayesian, uh, what is actually the Bayesian rule, okay, or Bayes. So let me interrupt here the sequence of presentations, and I will make sure that we are familiar or good with the concept itself, because now I realize I never defined what Bayes rule is. So I will quickly exit from this and okay, and I'll share. Okay, everybody's seeing the page, the website? Yes? Okay. Uh, so in the okay, that's the about no. Okay, in the schedule, or maybe in the release, in the schedule. Sorry. Yep. Uh, yep. I've added. Um, I think it was either some of this was today and some was yesterday. So if you haven't seen this before, reload the site. Um, just introduction to the basic concept of probability and cognition. Okay, so let me walk through this link. Okay. Just a second. Um, so of course I want to kind of go and read this exactly line by line, but it kind of explains the Bayesian brain hypothesis, and um, the idea is that you know, a principle of being able to infer something from the data that we have is critical for so-called homeostasis, which means uh, you know um, anything, especially living algorithm organism, sorry, has to balance itself with the environment, and in order to do this, it needs to do something in order to kind of to set itself to some underlying structure of the world which is outside of the system itself. So of course it can be related to physical and chemical processes in the living system that keep it basically structured and self-organization and so on. So it's kind of not loading the images, but I didn't realize that the internet connection would be a problem. there is an equation that I'm waiting to appear here. I can start writing this, but kind of the idea is that for any event that we see, basically, event means we have some data that you measure from the environment, sounds that we hear, um, data that we measure in scientific experiment. It might have some kind of underlying cause. It might have some kind of underlying structure, and the cause or this underlying structure and what we actually see in our with the senses or with the measuring device uh, are kind of jointly related. So um, you have kind of a probability that something caused something else. So while we kind of talk here, wait for the images to load. For instance, you can measure the relations between uh, having clouds in the sky and rainfall. And of course, you have some probability of having clouds, you have some probability of having rain. So everything is basically described as a random coin. And you have a joint probability that you'll have clouds and rain, and you have conditional probability, which means if you have rain, what is the chance that you will have clouds in the sky? Well, it's probably very high probability. So the whole Bayesian rule actually kind of describes how two things are related. In this case, the probability of having rain if you have clouds is defined. So this is just kind of a mathematical structure that underlies this probability type of reasoning. So the probability, so this kind of way of writing this down, that you have this line here, this is an existing thing, so this is a given cloud, and this is the probability of something happening. So they're both kind of random variables. There's both random occurrences. You can have clouds and rain. You can think about this chord and notes that correspond to this chord, okay, or certain distribution of melodies, given that you're playing. This could be tonality, and this could be distribution of notes, okay? So what is the probability that, given that you are in a situation that you have clouds in the sky, what will be the probability that you have a rain? In this case, you can see both, right? You can go out and immediately tell if if you're getting wet, there is rain. You can look up and see clouds. But in what we'll consider in a second, some of them are not measurable. You don't know if there are clouds in the sky. You can only see if there is rain. Okay. Let's say you have sensors that can tell you if the grass is wet, but you don't have a camera looking at the sky. So it could be that there are clouds, and then there is a good chance there will be rain. But the whole logic of reasoning, the probability, is that you have these inverse relations. You can have the probability of having, given rain, what is the chance of having clouds, times these probabilities of only having rain or only having clouds, okay? Separate, as like you just consider them as totally unrelated events. So in this case, the chance that if there are clouds, that you will have rain can be calculated from these other probabilities. The chance that you have clouds if there is rain, which is very high chance, and most likely if it's raining, there are clouds, and you just basically aggregate this data from examples. You basically measure both enough times to have these joint probabilities, a priori probability of having rain and a priori probability of having clouds. So let's say the chances for rain are only 1%, the chances for cloud are 10%, and if you multiply everything together, you actually see that you have a probability of given clouds to have rain being only 8%, right? So this is kind of what the logic goes. You have very high probability of having clouds if there is rain, 80%, probability of rain only 1%, probability of clouds 10%. If you do the math here, you get the overall probability of having rain given clouds only 8% chance. Now, why we want to do this? I mean, you can go and read this. This is more an example of false positive, false negatives, how you calculate all of these probabilities. So this article goes a little bit into the math, but then it kind of relates this to the idea of the Bayesian brain. So what is the idea of the Bayesian brain and how it's related to Bayes, or that kind of mathematical probability. So the idea is that you think that there is something in the external world and the internal world, and they're kind of separated. And this is where some of this is hidden and some of this is evident. Okay, and these two things are described as random events, and they're related or separated or related, depends how you look at this, by so-called the Markov blanket. So the concept of Markov blanket, and we'll repeat this concept. So I'm introducing a lot of terms here without fully explaining them. This is a nice introduction, but we have a paper talking about Markov blanket, and it would be great if somebody can kind of take and explain this more in depth. Is a basic idea that Carl Friston, who kind of used this idea of free energy principle for the brain, uses a lot. Okay, and basically the critical point of Bayesian brain, I'll just kind of read this paragraph, okay, is that the internal model of the world within the brain suggests that processes in the brain model processes in the physical world. This is basically how the relation between the function of the brain in some sense has an internal model of the world, and it exists in the brain, and then basically what the brain does, okay, it models the outside world. And in order to predict the future, the brain needs to run simulations of the world. And we'll kind of talk about this idea that basically the hallucination, the imagination, is something that we simulate the world that exists outside of us. So if you imagine or you create music or imagine something musical or you listen to music, you still kind of use your brain to create this virtual replica. And you always compare your imagination to the outside world. So given this idea, okay, I want to go back to the slides. Let me see if I can. I think I need to share them again. Can you see the slides now? So here's kind of the idea is that some part which is hidden, you can call it sometimes prior, and the evidence that exists in the world, you try to measure how likely it is, or what is the probability that something will happen, and you call it likelihood. So in this example, you're actually talking about somebody who comes to the forest, and this is the second link on the website. Somebody goes to the forest, he wants to take photos of a bird, and he wants to look for birds somewhere in the trees, and then he hears a chirp. Okay, there is a bird song. So then the question is, this is the new evidence, but he has a prior. The prior means he doesn't know where the birds are, so there is some kind of distribution. The blue curve is his a priori assumption about where the bird can be, and then when he gets some new data, he tries to adjust his prior beliefs to the data, to the perception that he achieves. So this whole process of going from some sensory information to understanding of the world, which in this case, sensory information is, I hear a sound coming from some direction, and then what your inference or the conclusion you want to do is, I want to see where the bird is. There is this process that goes from the sensory neuron to inference neuron, and you basically try to find the relation between some data that you get, let's say the sounds that you hear from a bird call, to you searching for the bird and finding this in a certain direction. So you learn to relate the direction of the sound to where you think the object is. So what you want to predict is basically find the bird, but your sensory input is the sounds that you hear. So using this kind of a idea of sorry, move forward. Oops. So this idea of taking some inputs, okay, which would be images or sounds or text, and outputting a decision. This is inference. Okay, so the inference goes through some kind of a set of decision steps, and this is kind of a typical model that neural networks use today. Is that you have these kind of neurons, and we won't go into the details of how they're calculated, but you have these kind of latent states, okay, which help you come to the decision. So you have an input map to a decision, and in some sense, you have some kind of a prior model. You have an understanding of the world that happens before you start collecting evidence and seeing if it's correct or not. And what we do is, and you have prior is this latent or hidden variable that is inferred in the learning process. So kind of the important points that I want to kind of introduce or make sure that they're clear now is these assumptions. That first of all, you have an outside world, which in this case is basically your sensory information, your audio, and you have some kind of an internal representation, which is could be in many layers, that eventually boil down the sensory information to some kind of a very abstract or very simplified model. And these are the concepts. So you can hear musical notes, or you actually hear frequencies. Okay, you have your cochlea basically vibrate in different ways and send um, these neural pulses up the brain, and at a certain point you actually hear either melodies or harmonies or rhythms, but what you have here are basically vibrations. So going from vibrations or sound acoustics to perception of music goes through this process of distillation, or this process of basically going into inference. So when we say inference, means that you basically find some kind of underlying structure that explains the world. Now, there's this other word, and I'm getting here a little wordy and technical, so please interrupt me.
Can I
Yes.
ask a question?
Yes, of course. Yeah.
So are you inferring this latent layer you talked before to subconsciousness, or more like a package of subconsciousness, consciousness, cognition, including memories?
So it's an excellent question, because this formalism has been adopted to questions of subconsciousness. It's not really so. We'll talk about consciousness as basically some way of matching your subconscious or your imagination to the evidence. But the idea is that there is some structure here, which could be thought as a memory, but it's
But memory is more like cognition, right?
It's memory in a very distributed way. You learn this by taking a lot of examples and being able to infer their structure. So I'm, it's an excellent question in the sense if, oh, sorry, go ahead, yeah.
All right, so it's more like memory in this layer. I'm just trying to.
Right. Well, I mean, the theories of memory in music are very, very, it's an excellent question. They're very important in the sense if this is a schematic memory or veridical memory, what are we memorizing? And so I would say, without going into, I don't think we understand exactly, at least in this formalism, unless you go and try to quantify this for a specific question. At this point, everything is encompassed in this. Right now, it's kind of a very, very high level approach. So there's something in the structure of the world that's imitated by this neural network. So a little bit more technically, basically, you assume that these neurons, if we want to look into this learning or biological analogy, usually you have kind of neurons that fire, and these links are basically like synapses. So the strengths of the synapses, you have all these excitations that hit on all these neurons. They integrate. So this neuron gets whatever firings it gets from these neurons. There's some kind of integration here, and it fires. And then this neuron might fire or not. This might fire or not from all these inputs. And all these neurons that fire will go next and next and next. And eventually there will be some kind of a neuron here. And it's almost a philosophical question. So is there like a grandmother neuron? If this neuron fires, do we recognize a grandmother? So the idea is not, it's not that this one, although in practice many times you do want this to say, okay, I learned to recognize my grandmother, so this is my grandmother and this is not my grandmother, or something, right? So you might think about this as a neuron that fires, but at this point, this is not the main idea I want to describe. What happens is that this whole thing becomes, and immediately we'll talk about this, you think about this as some kind of a generative model. And this is the big jump. Usually when you talk about neural networks, you start with a simple classification. And then in that sense, there is some kind of a pattern here. So if this neuron should fire when your grandmother walks into the room, and this one will fire if something else happens, right? You would say that there is some kind of an idea or whatever image the retina had here, which is decomposed into some elements. You recognize the facial expression, you recognize the body parts. It all kind of is decomposed and then combined together into specific recognition of grandmother. Then you would say this network kind of memorizes your grandmother, right? But we don't want to think about this really as a memory. It's kind of like this aggregate of features that eventually will allow you to recognize or infer something. And that would be the usual way of looking into neural networks, like a classifier, right? You give it a lot of examples. Let's say you train it on faces, and you give here the names of people, and you have a lot of different, photos of the same person with different angles, maybe slightly different times, age differences, and of course angles and lighting conditions and so on. And he, the neural network receives all of these images, and it's being told, yes, this is the same person, okay, person A, and then you give it a lot of other examples and of person B, and this will be neuron that fires in person B, and the network will actually learn this mapping from different pictures to labels. This is kind of the classical way of thinking about this. And only later you go into generative models. And usually in neural network literature, you get to this pretty late, because this is kind of not the point. You can actually build a lot of tools without thinking about them as generative models. And here our point as a Bayesian brain is that this is kind of a generative model in the sense that you can now trigger, you can put noise here, and it will generate images here. See, there is this process of imagination that can happen backwards, and we'll talk about this in a second. So this whole network, in some sense, encodes or simulates the world. If you think about this not only from left to right, but from right to left, you can think about this as a generative process. So you can train this to recognize things, but then you can kind of start, with random numbers. You can trigger these internal layers, hidden layers, and it will eventually create these hallucinations, basically. So the idea here is really something that normally you don't talk about when you start talking about neural networks, because usually you just learn these tasks, mapping input to output, or regression, or classification. But in generative models, you can actually think about this whole thing as a random number generator. That now you can start with deep structure, and if you think about this as something that corresponds to the thing that you hear or see, you can actually generate. You can generate images, you can generate sounds here. So in that sense, whatever is inside the black box is your hidden variable, and you need to kind of create some kind of a hidden structure here, so it will be correlated with data that comes here, and this is your interface with the real world. Okay, so this is the data, this is the real world, this is the actual music or the actual images, and this is the internal, whatever box it is. It's either your brain or a neural network or an algorithm. So this is kind of an important question, because what we get here, okay, I mean the data, the sounds, here's everything that comes from the real world. All whatever Beethoven sonatas. You want to learn Beethoven style, you will basically one by one show this neural network examples of Beethoven pieces. We don't know what actually happens here. We don't know how Beethoven generated these things. All we get is the actual sounds of the music. And here the network actually is a little bit limited. It has a certain structure, so it will try to approximate the structure of Beethoven by adjusting itself, by learning some structure inside. But of course, it won't be exactly matching the real data. This network maybe will learn something of their style, but it will not be able. We don't have Beethoven's brain here, okay? We don't have also all the knowledge of the culture or whatever it is that comes into these data points. It's just it's an approximation. So this is actually an important point, because this is what's called variational view of learning. And what it means variational, it means that maybe we have some observations O, and we have these states, hidden states S. And here I apologize, I kind of use a switch notations here just because I copied this image from somewhere else. So S is Z and O is X. But the idea is that this is what you observe in the world, and this is some kind of a latent or hidden state, S. And maybe the real world, has its own structure. It generates things from some kind of its own causal structure to create observation. And this is how the blue curve is really how the data or how the observations are generated so we have this basically joint probability observations and states. And here, this is your true inference. Basically, if you know the observations, you can infer the states, and this is how it's distributed. But the network can only approximate this by this different structure, which is much simpler. So the whole point of this graph is to say that the real world, which is the blue one, might be much more complex than what the green distribution is being. So the things that the network can imagine are usually much simpler than what the real world does. Okay, so this is variational view, which is important for things that we're going to say in a second, because we are trying to approximate the true world, which here is represented by P, by some kind of a simple or more simple model called Q. And this is where the variational thing comes. So when we'll talk about variational learning or variational models or variational inference, basically the philosophy here is that we want to build a model, and in this case building a model may be training our brain, training a neural network, okay, to approximate the outside world. So the outside world has observations, O, which is the sounds that we hear, the images that we see, and it has some distribution. So different sounds occur with different probabilities. Now, we assume that in the real world, there is also some kind of a hidden cause or latent, we call it the model, that the world is driven by some latent or hidden variable, and this is the Bayesian rule here. Okay? So bear with me, because I know this is math, but kind of the idea itself is you can actually start thinking about the relations between the internal structure or the causal things in the world and observations using this Bayesian rule. But it's too complex for us to learn. So we have some kind of a simple model, which could be our brain, could be a neural network, it could be the model, the algorithm, the right to create music, that tries to approximate this. So we're approximating this idea of relations between, you know, the hidden state or the latent variables and the observations, so between the internal structure of music and the actual musical notes. This is the true, let's say, if S is harmony and O are notes, there is some kind of a true relation that exists in Beethoven's sonatas between, you know, his logic of harmonies or his structures and what we see on the musical surface. But we don't know really what it is. We just approximate this with some kind of simple machine which tries to match this by learning Q that relates these two things. And we want to measure how well we actually are able to guess the internal structure, or how well our model can imagine this internal structure comparing to what the internal structure is in reality. So this is kind of the concept of variational view, means that we try to approximate this structure of the real world that has maybe some underlying cause and effect by a more simple model, which is going to be our composition. So what happens in the free energy idea? In the free energy idea is that you have this relation which we call energy and entropy. And free energy, and this is where kind of the physics, you know, the Helmholtz idea, which comes from physics, right? This is where the terminology comes from. This is the traditional physical definition of free energy. Free energy is an energy minus entropy. Now, we didn't really define what energy is and what entropy is, so my purpose is kind of to define these concepts, but translate them to musical or philosophical terms. So what is energy? The whole idea is that the system, okay, tries to decrease the free energy or increase the negative free energy. And when it does that, it tries to basically infer the hidden causes of the world. It tries to understand what's going on in the world. It tries to find this Dalmatian dog in the spots, okay? It actually feels that, you know, it tests all kinds of hidden variables. Its understanding of the image, that Star of David, that Dalmatian, or actually hearing things that we are familiar with in specific musical style from the examples, and it tries to improve its understanding of the world by increasing the negative free energy or reducing the free energy. And it has these two components to it, okay? It basically tries to go and search for the highest negative free energy, and this increases its probability of explaining the observation, explaining the world. So how it's done? It's done by changing its internal structure, okay? Increasing the negative energy by improving the model of the environment. So the process of learning is actually changing your internal structure, so the evidence that you see in the world will be more and more likely. So you will be basically expecting more, your predictions will be more correct. The images, the things that you see, the patterns that you recognize in the images are corresponding to some ground truth, some reality, okay? So this ability of you to kind of restructure your model, adopt your brain by learning, is explained by this principle as something where you basically have two different components here. And for those who are mathematically inclined, we'll talk, you know, I have a couple more mathematical slides, but this is basically kind of the idea that free energy has these two different components. You want to have the highest chance or probability for what you observe in the world, and you also want to match, and this KL is kind of a distance between what you guess is the underlying causes or the hidden structure, okay, the states in your brain, to the states that actually exist in the world for this observation. So this is kind of the whole game that we're playing here. Uh, we only see observations, we only hear sounds, see images, you know, read text, maybe have other perceptions, but there's this sensory barrier, right? This is what gives us the observations. Then there is kind of internal structure, which is the S that happens in our mind. And what we try to do is basically, we don't care so much about the sensory data itself. What we try to do is infer what caused this. So we assume that in the real world, that chirp came from a bird. So we're looking for a bird. We don't care about the chirp so much. The image came from a dog, so we look for a dog. We don't care so much about the image itself. So we try to find that hidden structure in the world, and in the world there is a true relation between that hidden structure, which is existence of the dog, and the image of the dog, right? And here is something that our brain tries to learn, which is guessing that there is a dog. So this idea that we want basically to always be able to predict the sensory information, and we also want to make a minimal error between basically our understanding or hidden concepts, or the states of the world and the states in our mind and the states in the world are these two things. And it can be translated mathematically to a slightly different way of writing this down, where we have the cost of our prediction is called the energy, and the distribution of the internal states is the entropy. And you can see that this rule, this double game of predicting the world, but also balancing this in terms of some kind of a complexity measure or structure of the internal system, which is measured by entropy, is actually the definition of the free energy. So this is kind of the core and the most difficult part of this whole seminar, is understanding why we talk about these concepts. And this definition or this division is actually pretty intuitive once you get used to it, because energy, you just think about this philosophically or creatively, is just a measure of how well you predict the environment. Okay? Entropy is a measure about some internal structure of your model of the environment. Okay? And you basically look and have these two penalties, or two different aspects, that you combine together and you call them free energy. So I think the first one is more intuitive, right? I mean, you have something happening in environment and you're able to predict this. So if you're wrong, I don't know, if you are not careful and didn't notice that the stove is hot, and you put your hand on the stove and you get burned, you didn't predict it well, right? You should have looked into some evidence. So it's pretty evident that you have a penalty by not predicting well the environment, right? You want to cross the road and you didn't look carefully, or you didn't estimate how fast the car goes, and it could be very.
Sorry. Can I ask a question?
Yes, of course.
Yeah, in the last slide. Yeah.
The one before?
Yeah.
This one. Mm-hmm. Oh, it's not a good sign.
Yeah, so my question is that in the formulation, in the KL divergence.
Mm-hmm. Yes.
So
okay, go ahead. Yeah, go ahead. I know. I'm trying to switch.
In the KL divergence, it formulates is QS in the front and the PS in the back. So I don't understand why, because P is actually the actual distribution of the world, but Q is your assumption. But why you use the actual thing to approximate what you assume. So in my opinion, it should be P in the front and Q at the back. So I don't understand the sequence.
Okay, let me see just a second. For some reason, I might need to restart the PowerPoint. With you, just one more second. Can everybody see now the PowerPoint again or not?
Yes.
Okay, so you were asking about specifically, right? It's a little bit technical question, right?
Yes.
Why we have it this way,
Yeah.
right? And I assume that you're familiar with the concept because this is not symmetrical, right? That was your question, because usually distances are symmetric. So how do you care? Why do you care if this is QS and this is PS or the other way around? So that's an excellent question, but just to try to explain this again, what we see here, okay, is some kind of a penalty or measure that tries to compare your assumptions about the world, right? About the hidden states of the world, right? And the evidence about these hidden states that occur in the real world, the P. P is the real world, Q is your brain, your mind, right? So you ask why we use it this way. You can also write this in a different way. It will be slightly written, the equation will be different. But the reason we write it this way is because eventually you think about the energy and the entropy of your mind. I mean, you are generating the imagination. So here, and for those who feel that this is too technical, just bear with us, and I'll move back to the higher level explanation. Here, you see the averaging is on the internal states of your brain. This is log Q of Q. This is the entropy of your mind, and this is why the KL can be rewritten this way. It's basically Q log Q. So you need Q to be the first one. And the energy here is, you assume that in the real world, the real world actually has this combination of the observations and the hidden states, right? There is some kind of underlying cause in the real world that causes the observation to happen, but the energy is the energy of the system, okay? So if you think about energy and entropy, it's the energy and entropy. Let's say if you had some kind of a gas, right? It interacts with the outside world. So it's the energy of the system and the entropy of the system. So it's the energy of your brain and the entropy of the brain. So this is why all the averaging has to be done on the internal states of your system. This is why it's all QS, and this is how this explanation is, how this math is written. So we can talk more specifically about how it's derived, and I have a slide later on. But the important point here, which derives from the way the math is written, is that you think about the uncertainty or the entropy, the amount of randomness that exists in your model or in your brain or in your algorithm, and the energy, which is basically, yes, you get your evidence, you get your data from the real world with P, but you average according to the states of your system. So this is why this was in front. It just kind of, if we want to use it, this type of relation to energy and entropy, this is how it's defined. Okay.
Thank you.
Sure. So these are like mathematically complex questions. So we definitely kind of have to go through them because the philosophical aspects are actually present there. And this is not really something that you would normally jump into like as I said, in the first neural network class or anything like this, these are really kind of pretty high level mathematical methods. But the intuition is really that you have this trade-off between predicting the data, predicting the environment, and the complexity of your model, which is measured by the entropy. Okay.
Can I ask you a quick, sorry.
Yes, of course. Yeah.
Oh, I just had a question about slide 7 and then 8, and it's kind of like follow up to the other question. So in slide 7, so it is we're intentionally making the area under Q to be small. Like we're intentionally assuming that there is a much greater variation in the real world versus the hypothetical one.
We intentionally, well, I think we have little choice. I mean, our model has limited possibilities. We assume that the world is more complex than what our model is. So we do assume that the model Q is just less powerful, that it only can capture some aspect of the true world. So it's intentional in the sense that, yes, you know, when we write the math, the Q will be actually the neural network can learn. So
Okay.
all possible distributions of the world that the neural network can approximate, or our brain can imagine, okay? We assume that they're less powerful than what will really happen in the world.
Okay, so it's not. It was not an intentional reflection of current restraints on the ability to calculate. So, like, if we were given a computer with like a much higher capacity, we would still. This is the theoretical models that we assume that our models are still going to be much less.
We assume that
Okay.
yes, yeah, we assume that it creates an approximation.
Okay.
It may be a very powerful approximation, but it's still kind of different from what the real world actually does.
And the difference between the P and the Q in this case, that area underneath, does not change. Like this is just a hypothetical. This is a theoretical model. It is not.
Yes.
Okay.
Yeah, it's just very, very conceptually kind of placed as the idea that the model can predict only Qs, and the world gives you Ps.
Okay, and then
there will be discrepancy between them.
Okay, and then the other question was just to in the next slide, the reason why the log is based on the Q is because we're using this as a model to reference our internal states. That's why it's it's subscript log Q and not P.
Yes, because
Okay.
everything is related to the model itself, to our brain, to the neural network. Yes.
Okay, and then just the one last one is that I was a little confused about the negative, increasing the negative free energy, and is that because the energy in this equation is assuming the total energy of the system, and it's just whatever, so that the energy amount is actually I guess it would be free energy plus entropy would be equal to energy. So we're trying to figure out free energy. That's why when we're saying increasing negative free energy, that negative part I think was what I was confused about.
Sure. No, so this is a great question, because it's just a source of a lot of confusion. For some reason, in the machine learning language, or the common thing is increasing likelihoods. So you talk about increasing either the negative free energy, which is the same as decreasing free energy. In physics, people talk about decreasing free energy, which is reasonable. You basically, every system wants to decrease its energy and increase its entropy, right? So this is what we are used to from physical world. Okay, you seek the free energy, you want to minimize it. For some reason, in machine learning, you just talk the opposite. You increase the negative free energy. It's totally the same. It's just the confusion in the way it was traditionally introduced into neural networks is. So I just want to make sure everybody understands that they're totally the same, just the language. Increasing negative free energy is same as decreasing free energy. That's just a source of confusion, but that's a common common way that in physics you decrease the free energy, and in machine learning you say I increase the negative free energy. But if you increase the minus, it's same as you decrease the plus. Okay, so that's just a source of confusion in the language people use in these different domains. But that's exactly the same thing. You can think about minimizing free energy or maximizing the negative free energy. Okay.
So is that to just decrease entropy? Is that another way of?
No, okay.
Sorry.
Yeah, no. I mean, it takes a while. Yeah, it's just the language is confusing here. Let's agree about one of the terms. Okay, you can either decrease free energy or increase the negative free energy. I think it's easier to think about decreasing or minimum of free energy. Okay, but it's exactly the same as maximizing minus f. So it's either minimizing f or maximizing minus f. Okay, it's just kind of the minus here makes things confusing, right? So if we think about this, okay, we want to minimize free energy, which means we want to minimize the energy. Minimizing energy means actually minimizing the error, okay? And we either minimize this, or because this is negative sign, we maximize this. So you have this kind of a trade-off between how well you predict the world and how complex is, not complex, how unassuming your model is. So you always want to have the simplest model, and I'll talk about this in the next slide. So you maximize the entropy and you minimize the energy, so the overall will be minimized. Does it answer the question? It's just doing the counting of what is minimum, what is maximum. Minimum of this is so minimum of the free energy, right, is minimum of energy. And because of the minus, it's basically maximum of entropy. So you want to maximize the entropy and minimize the energy. That's the whole assumption here.
So in this case, the entropy, like Angie is saying, is referring to the degree of complexity and not to the degree of randomness. Because I think I'm coming from a physics point of view, so I see, right. I understand entropy as like the level of complexity, but not in the way that I think this is talking about entropy.
No, I think it is. Let me jump to the next slide and continuing your question. So, I mean, you think about two things: is if energy is how well you predict something, okay? So your model is trying to best. You want to seek the best explanation for the world, but you also want to think about entropy in the sense of you want to have the simplest or the least assuming approximation of the world. Okay? So the idea of maximum entropy, if you think about all possible distributions or all possible models that conform to your measurements. You measure a few things about the world, and then you build a statistical model of it. You can build many different models. So let's say in this Copernicus example, right? What Copernicus did, basically, he wasn't the first one who could predict the motion of the planets. Right? Before that, there were models that actually assumed that the sun revolves around the Earth, but then any other planet had this very complex model that would be required. Now, in reality, if you propose a different model, which is much simpler, much less assuming, it doesn't mean that it will predict better than the complex model. It's just that the model itself is much more elegant. It's much more simple. The other principle of the Occam's razor, which exists in science, is saying if you have two different explanations, and in our case it's two different models of the same phenomena, okay? I don't know if you can see, this is slightly small, maybe I'll zoom in. I don't want to go into presentation mode. When faced with two opposing explanations for the same set of evidence, our minds will naturally prefer the explanation that makes the fewest assumptions. Okay, so the idea of entropy in this case is a measure of the least assuming model. um, if you have different models, okay, that still explain the world with the same level of accuracy, okay, and now you want to have some kind of a measure of the complexity of the model or how much structure there is in the model. From all the models that perform well enough, all the models that can predict the planetary motion, you now ask yourselves, okay, they're equally, their energy, in the sense of how well they predict the evidence, is the same. They both achieve good results. They minimize the energy. But between these two models, I want to choose the one that is least assuming, which means it has least structure. So in the statistical kind of thinking, if you have different statistical models that explain your measurements, okay, because you measure something from your data, you measure, let's say, the mean and the variance, okay, you can have many different probabilities that will still have the same mean and the same variance, or you extract some features from the world and you might fit it to many models. The one which is least assuming, it means that it has the least amount of structure, and in that sense this is the maximum entropy. So high entropy model is actually the least assuming model, or in some sense our brain, okay, that learns evidence. So maybe the best example would be how it's applied later on in some of the articles. You look into the evidence or things that happen to you during the day. Okay, you collected, you went outside, you saw things, you constantly learn, you constantly do this inference process. Okay, and by doing this inference process, you build a model of the environment. Okay, this model might be pretty complex. Okay, then one of the assumptions, actually one of the early algorithms that started this whole generative revolution in neural networks, had this wake and dream phase. So you collect your evidence, but then you need this kind of a dream phase to try to simplify the models. You actually try to find the least assuming model. So for instance, in the papers that, one of the papers that we have talks about the role of entropy is basically that the process of dreaming actually is a way of increasing the entropy. So the fact that you simplify, when you dream about things, you simplify the model that you had in the world. I mean, the model that you created in your brain from the evidence that you collected from the world during the day. Because if you don't go through this process of basically letting go from unrelated things, okay, you don't want to memorize specific things. You don't want to have very, very complicated models. You want to have the simplest model that explains your evidence. And the idea of from all possible things that you memorize, or all possible things that you learn, the simplest one will have the highest entropy among all the models. But here the idea is that the energy is constrained. They're all good models. It's just the least assuming model is the one that has the highest entropy, or the least amount of constraints, or the least amount of parameters. So if you think about this one, if you think about entropy as some kind of a count of complexity, okay? So in this model, okay, you have basically center and 2 degrees of freedom, these radiuses and speed. Here you have to create a very complicated model, okay? This model has a lot of structure. And because of this kind of very strange mathematical shape here, this is not a statistical model. This is kind of maybe a deterministic model, but you can still see that this one is more complicated. It has more structure. So the least amount of structure means the most amount of entropy in that sense. So if I can kind of continue a little bit, I don't know, my computer is having a lot of issues. Okay, I'll have to kill and restart. I don't know why PowerPoint is doing so much trouble.
Oh, Professor, I had a question,
Yes.
but
Yes.
is it better
Go
to
ahead.
ask? Oh, it was actually about earlier back. I was still thinking about this that question of I think it
Yeah,
seems
go ahead.
that the central thing is of representation, how there's some hidden structure and its energy is put into this system to organize it to reflect that hidden structure. But I was wondering, is there another, it seems like there's another model of phenomena like slime molds and leafcutter ants and these sorts of self-organizing systems where there isn't actually representation going on. It's just a sort of, there is no relation between the internal structure and the external structure, but sort of a signaling, sort of a distribution of the machinery, like over the two systems. So is that at all,
yeah, so self-organizing is one of the ways of learning, right? I mean, the system can kind of basically self-organize it to represent or mimic the evidence that it collects from the world. So in that sense, self-organization is a specific case of this principle. Now, maybe in this example, the next slide, let's say you have some kind of a real world distribution of these green and red dots. It's from, I mean, what I'm following is one of the blogs that is linked from the web page. And I think in that example it was apples and oranges or something, colors and sizes. So this is your true kind of distribution of a typical apple and typical orange. I'm not sure that's the right example. I mean, exactly what it was apples and oranges, but let's stay with this. This is where your typical apple will happen, and this will be the distribution of possible features in your space, whatever you're measuring, maybe the size and the color. And this is your orange, and this is the distribution of features. So your measurements are these O's. O's are two-dimensional vectors, right? Your evidence is here. You look at your model distribution, and this is what your brain tries to do. Your brain gets this data, and now it tries to create these ellipses to fit into the data. And the hidden states will be just the likelihood of having oranges and apples, okay, as these ellipsoids. So here's kind of summary of this whole idea is that an organism, basically tries to mimic the world, and you assume that the world has a generative process in it, okay? It has some hidden states that create observations, but we don't know what this distribution is. We only look at the observations, okay? Now, our brain takes these observations and creates its own model of the states, okay? So you have this process of here, okay, it's inference because you want to guess what is the state as given the evidence, but you can also go back and generate observations from the hidden states. This is kind of the generative part, and this is the inference part. So this is generative model basically means that you can flip these two things. You can have observations given the states, and the inference, you have the states given the observations. But part of the idea is that the whole idea of the model is being able to play with these encoding and decoding, these two different flipping, basically the relations between the cause and the effect, or the hidden states and the observations. And it simulates what's happening in the real world. So kind of the idea is that the living organism, to stay alive, maintains this homeostasis, which means avoiding surprising states, which means avoiding surprising observations. And this whole process is minimizing the surprise, or basically the approximation to that surprise is done by free energy. Now, why it's approximation? Because the P and the Q, basically here slightly the notation doesn't make distinction between P and Q, but this would be the Q, the internal representation, and this would be the P. So it's approximating the real world. So the brain avoids the surprise by actually creating this Q. This is what the world can imagine. Okay, and these are kind of the details of the math. And the surprise is basically defined as minus log of the probability. So if this is the probability of the evidence, okay, we want to have the most likely evidence, minus log, okay, so the relation here between these two graphs is that this is the probability of those observations, and the blue one is minus log, which is basically giving you the minimum, right? So the minimum of minus log P0 will be the maximum of P0. So this is just kind of another terminology that we'll see in the papers that might be confusing, but surprise and evidence. You maximize your evidence by minimizing your surprise. It's just making sure that we speak the same language. Surprise and evidence. Surprise, minimizing surprise is same as maximizing the evidence. And you do this by approximating this with a free energy, where the free energy is basically only some approximation to the real model. So the real model, you can have all kinds of models, okay? And you're basically trying to find the best model for the real distribution of the events in the world. But our brain is the red one. It approximates it, and you basically minimize the free energy, and you learn by trying to move this red curve lower and lower until it approximates best the world. But it's not the real distribution. It's just what your brain can approximate. I know it's a lot of conceptual ideas, and the math here could either help or basically push you away. So I hope you're fine with the ideas. The notation here, for those who are not used to it. So I will totally skip this math detail if you want. This is the for those more mathematically inclined. There's actually this exact definition of all these equations and how you end up with this expression of energy and entropy by taking this assumption that the world is distributed according to P. Your model is able to approximate according to Q, and just by playing or having these two different ways of playing with this equation, you end up with these two different ways of writing it. And this is basically equivalent to energy and entropy, or so this is the minus entropy and this is the energy. So I'll skip this because there is no point of going through math just to repeat the same ideas. But if somebody wants to see the derivation, I'm happy to do this offline. So I think this is kind of the summary. It was a long lecture, but I think it was important because once we establish this basic premise, the rest is kind of a lot of applications of the same principle, the same concept. So by minimizing free energy, okay, we have this trial distribution. But I say trial distribution means what your brain is able to approximate. Okay, so you have this kind of a imagination or approximations of ideas which are internal to your brain. Okay, and you have your trial distribution. You try to get closer to something that exists in the real world, where in the real world the S would be the underlying causes and O are the observations. Okay, so you try to match your internal representation to evidence in the outside world, and you operate in these hidden states. Okay, now if they match, this distance, the KL term, which is just this technical one way of measuring distance between distributions, becomes 0, and free energy is exactly equal to surprise. So if you really manage to learn the world, okay, then you basically are able to predict best what's going to happen in the observations, and in that case, our variational graph, the green graph, can exactly match the blue graph in the slides before. Now, the more we minimize the free energy by changing or wiggling or learning the internal representation, the more it becomes closer to the surprise. Okay, and minimizing free energy by wiggling the parameters can minimize the surprise even further. So there is this additional notion of just a second, and I see that what happened is that in the crashes I actually didn't get, I had an edited version of these things, and I think I got the previous one because I said don't. Oh, okay, I'll have to redo the slides because actually I posted a PDF, so luckily the PDF should have all these examples. Can you see the PDF now? Okay, I'm scrolling down. So yeah, so let me summarize this from the PDF. It's unfortunate. So what we have is, the PDF is in the Google Drive. Okay, so we have this following thing. Minimizing approximation to surprise, which is the free energy, is basically a way for us to avoid surprising observations, okay, which leads to avoiding surprising states, which means maintaining homeostasis, which means really remaining alive. So the summary of all this process is basically inverted here, okay? By following this principle, the system basically tries to adapt itself to the world. A couple of more things that I added here are that we try to choose the most unassuming model, the simplest explanation. This is the entropy maximization. And to reach this state can be achieved either actively, so you can either act on the world, or passively, like dream or hallucinate. And we'll talk about this thing because a lot of the Fristen's work about biology and biological systems and then brain cognition also has to deal with the idea that there is this aspect that we are free agents in the world. So not only we can adapt ourselves to the world, not only we can find the best model and the best approximation, we can actively do something to limit the sensory input. We can actually go and create a subworld, and create a niche. We can create culture that actually doesn't allow certain things to happen. So it's not only that we can learn and adapt ourselves to the world, and because our brains are limited, we only have an approximation of the world. Since we are active agents, we can do something, so our sensory experiences eventually will match our expectations. It's almost like self-fulfilling prophecy. So in one of the papers, one of the examples where he talks about market blankets and kind of the underlying principles is, I think, a fascinating example of C-squared. And what the C-squared is, this little sea creature. I don't know if people are familiar with it. That it lives in colonies. It actually looks like a plant, but it's actually a living organism. It has a heart. It has metabolism, and the thing is that the tadpole, or the early stage of that C-squared, actually has a tail that it can move and can navigate. It has a whole set of cells, like a little brain, that from the wherever that C-squared was born, it allows it to navigate and settle in a different place. And that's where they start building the colonies. And the interesting thing about this C-squared is that once it settles in its new world, its new environment, it actually kind of eats its own brain. It dissolves some of its functions. And then the question is, why would an organism basically give up on the complexity of the model or the complexity of the way it can approximate the real world? Well, the thing is, it actually manages to create an environment where it can operate because they live and they stay in colonies. And if they evolutionary somehow, if the sequence didn't eat its own brain, it could still keep moving, it could still go places, and it wouldn't be able to create these colonies of plant-like like coral reefs of these sea squirts. So it actively actually limits its world. It almost creates like an isolated and very limited niche where it can actually exist. So the idea is that we can actively limit, we can not only learn the complexities of the world, but because we're agents in the world, we can actually force the reality to be simpler so it will actually match something that we desire. And this is also a very kind of intriguing, I think very powerful concept that puts a lot of conventions, musical style, or maybe cultural conventions under this question of, are we intentionally simplifying and forbidding, or we're not open to some ideas in the world because we already have a preconception, we have already learned some things, and then we want to enforce it on everything else. We actually ignore evidence because now what we care is maintaining our internal structure, and it's actually more important for us than actually looking out there and seeing what the reality is. So so that's kind of a very, very interesting concept that I think would be fascinating if you could explore this musically, is actually how staying loyal or remaining loyal to certain musical conventions or musical styles actually limits the range of musical expressions. Okay? How something that, the concept of, not only dissonance, consonance, of a musical error, right? False note, right? It's actually related to musical style. So by already learning a specific musical style, we already have a model of a very specific subset of things that can happen in the world. And then if somebody comes with something else, if there's new evidence or something new that is created, we can actually deny this. We can actually think about this as an error. We're not open to creating this kind of music because we are already fixed into a specific way of thinking and perceiving things. So I was kind of hoping, but okay, I'll have to redo the slides. It's very frustrating. There was an example. Let me see if I can bring it up. Of the idea that things that we learn kind of force us to perceive the world in a specific way. I had it also in one of the other slides, in one of the other presentations. If I can, sorry about that.
So, Professor Devnov, other question.
Yes.
Is this really been connections made to things like selective auditory attention and music perception in that sort of vein? Is there connections there between surprise and how short-term memory of what we've just heard, and also long-term memory of maybe one's training, like if one is trained to listen to certain syntaxes, whether that's been integrated with this view.
So There was a little bit of noise, so I hope I understood your question right. I think what you're asking, if things like learning specific musical skills or memory is related to this idea of free energy. Yes.
Oh, sorry.
Mhm.
Let me just go to
Can you ask it again? Sorry, I wasn't sure. I mean, definitely, whatever we learn creates our expectations. So when we try to you know react to content that we hear, or we want to create music in a certain way by manipulating the expectations or creating surprise. So validation and violation and validation of expectations is considered as one of the tools that composers really use. So part of this is really being able to manipulate the predictions and creating surprises. But it assumes, of course, that you know, if I understand correctly, the question, or at least the way I interpret this, would be for the listener. So the listener, for the listener to be able to sense the same surprise, or be able to even have emotional reaction to, let's say, a false cadence or any kind of appoggiaturas or sustained notes or tensions. He needs to have this notion of the fact that this is not expected. And when it's not expected, the question is, where did he get the expectations from? So to have these expectations, he had to be exposed to a lot of musical examples. So this entrainment or enculturation has to happen before you can actually communicate this musical emotion to the listener. So in a very broad sense, and maybe a little bit too broad, this Friston, when he speaks about the principle, the free energy principle, he claims that it explains everything. But once you start breaking this into specific examples, there are very many different details and questions that could be addressed differently. Right? So, what exactly is the memory? How exactly do the prediction? What are musical schemas? Each one of them is a whole area of research. The free energy principle is, in some sense, tries to give this underlying, all-encompassing principle of where these things came from. Why would an organism create schemas? Why would an organism want to create expectations? So, so I think we will continue a little bit the discussion also next week. It has been a long day and very intense. So I will also send an email kind of to a little bit adjust the schedule, because I think we want to start meeting and looking to the papers, but I didn't have a chance much to go over the papers. So I'll communicate about this in the email, and maybe send a little summary of what the papers are, so to facilitate you in selecting the papers for next week if we start scheduling individual meetings. But before going there, and also I will review the chat in a second. So just one more example, which I think can help. This is not the right video example. Yes, can you see this thing saying your world is only a hallucination? Or I'm not sharing the right slide. Yes. So this is an example of of a work that actually I had it in my video example, so I don't remember exactly the paper. I can find it. It exists online. So I'll play the example and just tell you a little bit what it is about. So this is so somebody took a neural network that was trained on dogs. For some reason, there are very many examples of dogs in training data sets. So it trained a visual neural network on a subset, and then what it did, it actually took a normal video, passed it through the network, and then reconstructed it back from that network that actually was trained to find dogs. And what this idea demonstrates is that if we want to look and we're trained to find certain patterns in the data, we'll be able to see them even when they don't really exist. We just look for a little bit of an evidence. So I think this is really a fun example. So let me play it, okay? So what this example is meant to demonstrate is really that if the network is really trained to pick up certain features, the amazing part was here reconstructing basically the full image from the network activations. But whenever the network was so sensitive that it could see dogs in its internal states, and then it was basically run back and generated the sensory experience. This is kind of what that network sees. It actually sees dogs anywhere, and kind of the idea is that in order for us to perceive something, we need to be able to imagine it. So if you think about the brain as some kind of a generative model that always triggers expectations, that's kind of the Bayesian brain. It has the latent states, but these latent states always trigger basically the observations. These are observations which are generated from our imagination, and we match them with the real observations. So we always hallucinate, and the data basically controls it. So kind of the consciousness is this balance between what we can imagine and what we can actually and what we actually perceive, and it has all these philosophical and possibly creative implications, because it would be lovely to have a musical example like this, where you train a network to recognize specific types of sounds, and then you pass maybe or take another acoustic effect or another piece of music, and it finds specific things. It almost like resonates, but on a cognitive level, right? It has like a filter tuned to be a dog, and anything that passes through this filter rings as a dog, even though it's not there. So this concept, I think, is fascinating, because it means that for us to perceive something, we need to be able to imagine it. And it also has this other implication, is that if you cannot imagine something, you might not be able to perceive it. So maybe there are things happening in our world that we are simply totally blind to them just because we were never trained to see them. And then we basically consider them as noise and we ignore them. So it kind of opens up this whole question about culture eventually. So we were talking here about really learning patterns, estimating, observations from states, right, or evidence, trying to maximize the evidence. But you can think also about society as a big learning mechanism, right? And then the question is, does society create these expectations that we actually enforce? So all of this, I think, is kind of a fair play for this class.
Oh, Professor, I was going to comment on that video. I wonder if a similar music example might be listening to a fragment, sort of like, I don't know, Steve Reich, they come out or something, and then after a while you start to hear that everywhere, or it just sort of trains your short-term memory, and then you see that everywhere. And there's some, I wonder if there's music perception that relates to.
So I think so. I think this is a very good example, and unfortunately, a lot of these papers don't deal with music. I mean, only from the free energy papers, I think there are only few that actually deal with musical examples. But and the fact that you memorize something, well, the question is, why would you hear it everywhere? That means you have some kind of random noise going in your brain that triggers these memories, right? There is a general, so it's not only storing patterns, right? It's also something that triggers them. So in that sense, I think the fact that you can hear this piece everywhere is because there's something that triggers that memory, but that memory is translated to your perception, right? It's not just a classifier. It's not just saying, oh, you know, there was an excerpt here that might have been related to specific, you know, technique, compositional technique or rule. You actually hear that, right? You actually hear that piece. So you kind of imagine maybe things that were not in that piece because your memory basically takes over the actual music. Or you can think about another example where you know, you just sit in a quiet room, right? And suddenly you hear things. You know, even John Cage's 4 minutes 44 seconds, some of the interpretation is, well, you listen to something, right? You can listen to the noises of the environment. You can also listen to your own imagination, right? So maybe that's the music, right? You sit in either in a quiet room or you listen to white noise uh, through headphones, and eventually you do hear music. So maybe before that, you play some kind of a long loop of music, repeating and repeating and repeating, and then the next section is there's just white noise, and you actually hear maybe something from that music. So it's going to be very interesting to play with these ideas because you kind of entrain the network, you create a structure, and then some random unrelated stuff generates your perception, which is basically hallucinated.
So does this kind of phenomena also shape like our way or like even like audience ways about certain like expectations? Like I was
yes,
just I was just
yes.
thinking about like something like, you know, in the memory happened like also you said about culture and also think about music. I was just like imagining just a small example, like for example, like a leitmotif thing in opera. Like certain things happen to that, but when that character come out again, like people kind of when they're used to that like motif settings of that thing, like okay, this character or the thing have to matching with certain phrase, so they have that expectations about having that thing to come out, just like, you know, matching the certain common areas of these images.
So definitely, so one of the papers actually tries to explain prediction in music using the free energy principle. I mean, you can think about this also as some kind of a just prediction, right? The ITPRA model, like David Huron's sweet anticipation, that talks about the idea that, you know, music is actually built by creating anticipations and then either validating or violating them, which goes all the way back to Meyer and musical emotions and stuff. They spoke about this, they just didn't speak about this in the framework of free energy as this whole process of the brain actually operating this way. But as a phenomena, yes, I mean, definitely you can use this kind of conditional probability or expecting the continuation based on the past. So kind of there is this process of you have some kind of either past musical material or maybe some outside evidence like a character appearing that creates your next step, your imagination, your prediction of what's going to happen next. And then when this true event arrives, you now match this to your prediction, and big discrepancy creates actually tension. So the whole idea of validation or violation of expectations assumes that there is a generative model, or there is a model that actually that you have a probability in your mind. So I mean, we kind of don't think about this conceptually, or we kind of just think about this, take it for granted. But actually, why would you have an expectation? That means you have a simulation running in your brain that predicts something, and then when that prediction is matched with the actual sensory input, you can compare them. So the whole process of kind of looking into the internal structure, what kind of model you would build, and the idea that the model has to be simple actually. So part of the process is actually finding the most simple expectation or most simple explanation or structure that will predict you the next musical bar or the next auditory event is kind of addressed by looking into this free energy concept. But yeah, definitely the specific or a lot of little, or not little, very important aspects of musical cognition already exist and existed before Friston came with this brain principle of free energy. And just as an anecdote, or to give a perspective, this principle was formulated in these deep neural networks by Hinton before Friston took it to the brain theory. He actually built on some neural network theories and then brought it to the neuroscience domain and then to psychology. And then he actually kind of created a great following of people who look into the philosophical aspects of this principle. But the principle itself, that a little machine can learn by creating this model of the environment and simulating and creating predictions, was actually done by neural network people, specifically Hinton. And that was the big revolution of the neural networks that actually led to the deep neural networks. So Hinton kind of, there's a video where he's a little bit kind of ironically saying, oh, it was just like one of my early ideas, and I continued to do other models, and now Friston is making all of his career from this one idea. But Friston actually managed to kind of formulate this as a very big principle. And I think the ability to look from this perspective into a lot of other phenomena that exist, because it's not that he explains them, he kind of unifies them. So he unifies ideas of expectations, he unifies ideas of even psychiatric disorders, right? It just gives a different explanation for phenomena that before that were explained in a very using very similar tools, but not in this all-encompassing theory. So
yeah, I just think like as an artist, I'm overthinking like what kind of opportunities like those principles and ideas can create in the different ways. Thanks for the explanation. That's very helpful.
Well, I mean, this is where I'm excited about the seminar. It's actually seeing where you take these ideas. I don't expect you to kind of work on the equations. We'll kind of look into a lot of these different articles from different perspectives that take these principles and apply them to other areas. But then that could be the bridge to creating a musical instance of something that was inspired by this, or more formally, less formally. I think that's the option. Okay, wow, we actually ran the whole 3 hours. Okay, well, thanks for hanging out with me. It was hard. It was a lot of material. So if somebody felt that this was too much, please give us more chance. We'll start working on the papers. So let's do the following. Maybe not tomorrow, but I'll try by Wednesday. Maybe also, and I kind of wrote down maybe where I think your interests reside. I will try to look again through the papers and maybe do a sub-selection or maybe suggest a couple of papers. Of course, you're free to go and look through the abstracts and see in general. There are a couple of very long papers which I would keep for the end. There is this paper about the culture that I sent initially to kind of maybe steer interest. This is a very well. The paper is not so long, but there's all these follow-up discussions. 75 pages. I would leave this to the end. I think the aspect of culture is super interesting. There's also another philosophical aspect about where cognitive science goes and brain science goes, which is also like a 70-something pages. It's a paper with a lot of follow-up. I would leave this maybe to later on. I think it's overwhelming to take them as a model, of course. But you're welcome to kind of look through all of them. So I'll try maybe to have a little summary or a little kind of suggestion of what subset of papers could be interesting. But let's try kind of to browse through them and not take them too harshly. If they are if they're too technical, just skip to another paper. And then what I think we could do the best would be to meet individually, and if you can select a couple of papers that are possibly interesting for you, give me a heads up so I can be a little bit more ready to discuss them also. And then I would like to meet individually in the next 2 weeks, and then we'll meet together and talk about these papers, and we'll figure out in the next 2 weeks how we want to address that. I mean, are you going to present these papers, or we can discuss them in a less formal way? So that would be maybe our plan for the next 2 weeks individual meetings, and then discussion of these papers in the group for the following 2 meetings. And that will already land us pretty much in the middle of the quarter. And then I would like to move to projects. So hopefully from the first half of the quarter, we'll be able to distill enough interesting ideas that will be then translated to these creative realizations, and that will be the fun part. Of course, also even more challenging, but we'll have to deal with the uncertainty. So we'll try to create some structure and ideas in the first half, and then create a lot of randomness and within that structure in the second half. If we consider this as kind of metaphor. But yeah.
I have a question.
Yes. Yeah.
So for the papers,
Mhm.
would you prefer that all of us try to read different papers, or if like some interest overlap? Do you mind like some people reading the same articles, or?
So at this point, because I don't want to assign the papers, I will post something, maybe some suggestions about what would be more of a artistically or psychologically inclined papers. But I would say if you can individually browse through the papers and maybe either find one that really resonates, and then of course the question will be what happens if many people land on the same paper. So I would maybe suggest that you find, I would say, your first choice, second choice, and maybe third choice, and then we'll kind of try to negotiate so we'll have a nice spread of papers. But again, we won't cover all the papers, and then if more than one person wants to present the same paper, we'll talk about this, and yeah, that's also a possibility. So I think at this point, don't worry about if somebody else wants the same paper. Just make your selection of the paper that you want to read, and maybe have an alternate possibility, and we'll discuss this next week in individual meetings, and figure out then which is which paper you're actually going to focus on. Does that sound okay?
Do you define somewhere on the website what the presentations are, or are you going to do that later?
Well, I don't want to be very formal about the presentation. I thought that something that I could imagine would be, because the presentations, and we are talking about the presentations in week 4 and 5, right?
Yeah.
The first set of presentations, not the projects. I would say few slides that summarize the main ideas, so we have some kind of a visual aid, and of course if there are some examples that would be great to show, and then a discussion. So kind of a summary. I would say we cannot have more than like about 15-20 minutes per presentation if you want also to leave some room for discussion. So really concise summary of the main ideas, and maybe advocating why this idea would be interesting, and we'll kind of discuss. So I did not really insist on a specific format, and I'm open to your own suggestions. But I think it helps not just like talk about the paper that other people maybe didn't read, but also have a little introduction and summary of the main points in a slide, a couple of slides.
Great.
Okay. I'm just trying to browse through the chat. So allow me, okay, so let me kind of go through these questions. I think they should be saved in the chat, and I'll try to answer them offline, okay, because it's hard for me now to go through them and kind of remember if I answered this, some of them or not. So if there is some question that was on the chat that I didn't answer and it's you know, important to talk about now, just let me know. If not, I'll check the questions and discussions and try to answer them. Yeah, when I'm less tired, maybe.
Hi, Professor. I had a question. Just sort of going back. I'm not sure if it had gone through, but it was about whether there's much research connecting work in like music perception and I'm thinking like Diana Deutsch or this sort of area of work to things like expectation and surprise and whether, well, maybe I should just leave it at that. Just that sort of vein. Like, is there a music perception basis for approaching the design of these, like auditory signal processing seems to really, help.
Right. So there is this approach which is kind of very much related logic, but it's not necessarily formulated as free energy. Although you know, as much as there is a Bayesian brain idea, there is also the predictive brain, which also falls under this general idea that the active inference is making predictions. So now, when you think about this approach of trying to do predictions and quantifying surprise, without calling it free energy, there is this whole area of so-called music information dynamics, which is a work that I've been engaged in, and there is also a group in London, in Queen Mary, and then Marcus Spears, and then Gerard Widmer, who moved now to Netherlands. No, sorry, Belgium. Continues this work. So there is one paper which is has this very funny name, and I don't know if I have a paper also called music information dynamics as surprise, or something, cognitive model of surprise, that I'll be happy to drop there. But there is a paper by Gerard Widmer, which is called, it has this strange name. It's so there is the information dynamics of music, which has this acronym IDOM, IDOM. So the whole concept of information dynamics is actually trying to use these probability distributions to try to explain surprise. And then with Gerard, he has this other model that the acronym sounds even worse. It's information dynamic of thinking. So it's IDIOT, okay, IDOT, and where he tries to take the idea of information dynamics of music and even generalize this to the principle of this is how we think, okay. But yes, so there is indeed a very formal kind of approach to thinking about musical expectations by using information theory and probabilities and so on, which very much falls under the same premise, like the free energy. unrelated, there is this work, I would say the most canonical collection of papers is by, that's the Sweet Anticipation by Huron, David Huron from Ohio. And he was investigating a lot, this question of how musical schema create anticipations and how musicians use this to create violation and validation of basically musical experience. Steve McAdams from McGill also was working on these questions of surprisal and familiarity, actually. This long-term and short-term structure versus long-term structure, which would be familiarity perception, versus emotional force, which is kind of, emotional force is kind of related to short-term surprisal. So yeah, definitely there are. Again, it's not as unified theory. I think maybe the closest attempt to unify this would be this information dynamics in music approach.
Yeah, yeah. That seems to be a very that seems to be sort of a common point or shared area or intersection between those like the actor project and these sorts of yeah, I'll take a look at that. Thanks.
Yeah.
Yeah, information dynamics.
Great. And yeah, so I'll point more specifically to these, in when I'll do a little summary of the papers and try to relate it to these specific questions of information dynamics also. Okay. So so I think Janet, you had a question about what the example of C-squared was for. I think that was more for the notion of actively acting on the world to create, an environment where you will limit your sensory inputs to something that you want to be able to predict. So kind of eating your own brain is an example from one of the papers. So you can increase your knowledge to minimize surprise from the real world, or you can actually limit the world so it will match better your expectations. That's kind of the idea.
Thank you.
If expectations and reality match, yes. I mean, basically, if your expectations and reality totally match, then yes, everything is, you minimize it to zero. Yeah. So about the sign, so the free energy is actually, it has to be positive, and the minimum would be zero. The negative free energy would be maximized and will reach zero. Okay, so it doesn't become negative. It just goes. The free energy itself is supposed to be positive, and then both of them will be zero. Okay. Let's go.
Sorry, didn't you say earlier that you can increase negative free energy?
Yeah. Right. So it's just a question how you think about this. You either increase the negative free energy, or you minimize the positive free energy.
Okay, so
the minus there is just a source of confusion. It just, for some reason, this is how the literature talks about this. In physics, you talk about free energy. In machine learning, you talk about the negative free energy. So in physics, you minimize. In machine learning, you maximize. But eventually, yeah, I mean, if it's negative, then it's negative and the maximum will be zero. Then if it's positive, then the minimum will be zero.
Okay, so like negative free energy, you didn't mean literally like negative below zero. You just meant like decreasing.
Well, because it's negative, you increase it and then it reaches zero because it's negative. I mean, it's either you maximize the negative free energy or you minimize the positive free energy. the minus and the plus there is just a convention. It leads to confusion, but eventually, if you look at the wording, it means the same thing.
Okay.
I think it's easier to think about minimizing the free energy, but
Then zeros.
and then the zero will be the minimum because the free energy is positive. So you minimize it to reach zero.
Okay.
We can actually go back to the equations at a certain point if you want. Okay. Well, thank you so much, and in French they say bon courage, which means have courage or good luck, and yeah, and send me emails in between, and if not, I'll just follow the Excel sheet and schedule our meetings. Okay, so just put in your name and time that you want to meet and some papers after you review them. All right, thank you guys.
Thank
Thanks.